Well, hello, everybody. Thanks for joining us. My name is Bruce Fathers. I'm the product director for Powers, which is a part of Watts Water Technologies. I've been in mixing for 20-plus years. So let's get started with the presentation. Watts Water Technologies is a global provider of plumbing, heating, and water quality solutions for residential, commercial, industrial, and municipal applications. Our mission is to improve the comfort, safety, and quality of life for people around the world. The Watts Water family of companies is backed by more than 140 years of engineering excellence and innovation. We are a publicly traded company on the New York Stock Exchange with deep roots in the industry. Watts Water remains committed to delivering innovative products to the plumbing industry. Today I'm going to talk about the next generation of water mixing for commercial and institutional facilities. I'll focus on the digital approach and how it makes tempered water delivery both safer and more efficient. Why is it important to control water temperature? There are several reasons. For one, today there are more people than ever living and working in very large buildings. They expect to have access to hot water whenever they need it. In addition, many green building rating systems are addressing water conservation. One, for example, requires that a design engineer create a preliminary water and energy budget. Adhering to that budget would require a way to precisely control water temperature. Another reason to control water, the people who design and manage facilities have the responsibility for making water available in a safe, consistent way that limits the risks to building occupants. And what are some of those risks? Two of the most important ones are Legionella and scalding. I'm sure you've seen news reports of the recent outbreaks of Legionella in cities across the U.S. We'll look more closely at how water temperature plays a role in controlling Legionnaires disease and other waterborne diseases during this webinar. So it's clear the need to control water temperature in commercial and institutional buildings is critical. In this webinar, we're focusing on the hot water delivery requirements of commercial and institutional buildings. That includes healthcare facilities such as hospitals and nursing homes, hotels and resorts, educational facilities such as dormitories and sports stadiums, office buildings, and prisons and jails. What they have in common are large populations with diverse requirements. That makes hot water delivery particularly challenging. Stringent control over temperature is needed to meet their needs. Before we talk about controlling water temperature, let's briefly discuss some of the reasons water temperature fluctuates. One is seasonal temperature changes in cold water supply. From summer to winter, for example, water temperature can vary significantly in some regions. A building engineering crew or maintenance personnel might adjust an upstream master mixing valve in response to complaints about the lack of hot water or the water being too hot. Whether adjustments are authorized or not, they can cause water temperature swings within the system. Master mixing valve failure can also result in water temperature fluctuations, as can system pressure fluctuations based on changes in demand. If a boiler or hot water heater malfunctions, water tempering will also be affected. I know of an instance where this type of failure created unsafe water temperatures in a nursing home. Improper valve selection can also create problems. Valves that are oversized have difficulty controlling water temperature at lower flow rates. A less than optimal hot water recirculation design can cause temperature fluctuations as well. And finally, improperly maintained valves can contribute to water temperature variations. Poorly managed water doesn't just create inconveniences. It can pose serious risks to health and safety. For example, uncontrolled and unmonitored water distribution systems can lead to too high temperatures and create scalding hazards in bathtubs, sinks, and showers. A rapid and uncomfortable change in shower water temperature can cause thermal shock and result in a fall or serious injury. And according to the Centers for Disease Control, the proper maintenance of water distribution systems is key to preventing illness from waterborne bacteria such as Legionella. For that reason, managers of commercial and institutional facilities need a reliable way to select and control proper water temperature in their storage and delivery systems. And then there's the inconsistent delivery of water temperature as it affects user or customer experience, for example, in a hotel. The hospitality industry wants to provide the best possible experience, which includes providing water at a temperature the customer expects. Let's look at these risks a little bit more closely. The American Hospital Association reports that there are more than 100,000 scald-related injuries every year. The most vulnerable people are children under the age of 5 and people over the age of 65. Thermal shock caused by sudden drastic changes in water temperature can cause a person to slip or fall and result in a range of injuries. We are all aware that the baby boomers are getting older, and the number of people in the 65-plus segment of the population is increasing. Currently, there are a little more than 50 million people in that age range in the U.S. By 2050, that number is projected to be approaching 80 million. That means a large segment of the population will be made up of people at increased risk of suffering scalding injuries and susceptible to Legionella. And as we all know, scalding water is very dangerous, and I have a few examples to illustrate that point. Hot tap water scald burns cause more deaths and hospitalizations than any other burn caused by a hot liquid, and we've cited just a few cases here. Some are due to mechanical failure. Earlier I touched on the importance of maintenance. In a nursing home in Pennsylvania, a nursing home shut down temporarily after a boiler malfunctioned and sent scalding hot water throughout the facility. Human error can also lead to scalding. And it's important to note that it doesn't take long for scalding water to cause serious burns. At 120 degrees, water can cause a first-degree burn in just 8 minutes. At 130 degrees, it takes only 30 seconds. And at 140 degrees, it's almost instantaneous. Water will cause a first-degree burn in just 3 seconds. We've heard a lot about Legionella in the news lately, but unfortunately those types of stories are not uncommon. Annually, between 8,000 and 18,000 people with Legionella are hospitalized in the U.S., and only about 3,000 cases get reported to the CDC. Cases of the disease were recently seen at San Quentin and Rikers Island, a West Coast prison, and a New York City jail complex, as well as an Illinois prison. Other commercial institutional facilities where Legionella broke out include the South Bronx Hotel and an apartment building. In the Bronx, 12 people died and 128 people were infected. Dr. Matthew Moore, a medical epidemiologist at the Centers for Disease Control, described the situation this summer as par for the course. In other words, the numbers are not particularly surprising. So the question is, how can we minimize the risk of Legionella? The best way to start is to understand how it's contracted. Bacteria can grow in a plumbing system with water temperatures of less than 122 degrees Fahrenheit. The ideal range for bacteria growth is 95 to 115 degrees. For that reason, many standards organizations recommend water be stored at 140 degrees Fahrenheit or higher and circulated at no less than 122 degrees Fahrenheit. They also recommend thermostatic valves be used at the point of use to protect against scalding. These guidelines address the need to elevate water temperatures to mitigate the risk of Legionnaires' disease. A new standard, ASHRAE Standard 188P, provides some protocols for dealing with Legionella after it is detected in a plumbing system. So to summarize, to protect bathers and other users of water, it's important to look at the plumbing system in commercial or institutional facility from the point of source to the point of use. From the boiler to the fixture, there are a number of devices that minimize risk. At the boiler, there are ASSE 1017 listed devices, typically larger valves and systems that distribute large amounts of mixed or tempered water throughout a facility. At the point of use, there are ASSE 1016, 1069, 1070, and 1071 listed devices, which are found at the shower, at the laboratory, and at eye wash and drench shower stations. Together, these devices take a comprehensive approach to protect a facility against these risks. Thermostatic master mixing valves are used to mix hot and cold water to provide water at a stabilized temperature. A thermostatic mixing valve, or TMV, compensates for variations in temperature and pressure. Water mixing technology evolved through the 20th century, but at a relatively slow pace. The first high-capacity mixing valve was developed in 1919. Then a recorder was added 20 years later. Then at the turn of the century, Powers introduced the Paraffin Actuator to master mixing valves, and it became the more dominant, more effective way to regulate temperature. The temperature within the valve is affected by fluctuations in the inlet water temperature. Heat is then transferred through the walls of the sensor and passed to the media. In the example illustration above, it's paraffin. Some manufacturers use ether and others use bimetal coil. They all essentially work the same way. The transfer expands the media and changes the ratio of hot to cold water in the mixing chamber. As the temperature gets warmer, the piston moves up, closing off the hot water and opening the cold to maintain a set point temperature. Today, the most common way to manage delivery in the mechanical room is with mechanical thermostatic mixing valves. In fact, in about 90% of the buildings, that approach is used. Thermostatic mixing is good technology, but as we discussed earlier, more demands are being placed on water tempering, especially in buildings with large and at-risk populations. So a more capable approach is needed. Many of you may be familiar with TMVs and are specifying them in your designs, so you know their performance requirements. They are most effective under ideal conditions. For example, you need relatively equal inlet supply pressures. Ideal conditions also means that the system is properly piped to the diagram and properly balanced. TMVs are subject to temperature creep in low or no demand periods, which occur typically overnight. Components throughout the systems, such as the TMV itself and pumps, must be properly sized. Some of the ways to optimize TMV performance include doing regular checks and maintenance. TMVs tend to be more susceptible to problems caused by water chemistry because the actuator is immersed in the water. And finally, minimum flow based on sizing can also become an issue. Valves need to be sized properly because larger valves at lower flows can have difficulty controlling temperature. So now let's look at the requirements for the sanitization process, which is typically performed in healthcare facilities. Mechanical and digital mixing valves have different requirements. One of the critical factors in mechanical mixing is approach temperature, and that can vary by valve anywhere from 5 to 20 degrees or even more. It determines the highest mixed outlet temperature the valve can deliver based on the hot water inlet temperature. So if you have a hot water inlet temperature of, say, 120 degrees, at a 20-degree approach temperature, the maximum amount of hot water you'll be able to get out of the valve is 100 degrees. With a 5-degree approach, you'd be able to get 115 degrees in a much more efficient scenario. In digital mixing, the hot water temperature must exceed the sanitization temperature by 2 degrees Fahrenheit. So if you have a sanitization set point of 165 degrees, you would need a hot water supply of only 167 degrees. With a mechanical valve, depending on the design and particular technology, you could need a hot water supply as much as 185 degrees. So you can see the digital mixing approach is much more energy efficient. With a mechanical valve, once you've gone through the process using the appropriate protocols, it's an imperative that the facility make sure that the fixtures at the point of use are not used while water purging is in process. After the process is complete, the mechanical master mixing valve needs to be reset and the system rebalanced. With a digital valve or system, the resetting and the rebalancing occur automatically. ASSE 1017 is the standard that governs performance for large hot water distribution valves. With mechanical valves, temperature regulation is based on valve size. So for larger valves, those greater than 40 gallons per minute, the standard requires that a valve must hold plus or minus 7 degrees from set point. So if the set point is 140 degrees, the valve must remain within 133 to 147 degree range to meet the ASSE 1017 requirement. Digital mixing is different because of its high response sensors and high-speed actuation and its sophisticated control algorithm, and can respond to plus or minus 2 degrees Fahrenheit. So instead of the 14-degree range of mechanical mixing valves, the control spread is only 4 degrees Fahrenheit. This is especially beneficial for healthcare facilities like hospitals and assisted living, as well as schools where tight temperature regulation is critical. Digital water mixing incorporates a programmable valve or system to process temperature, flow, and pressure data, which is obtained from inlet, outlet, and return sensors. There's high-speed electronic actuation, which operates a fairly simple ball valve, allowing set point to be maintained. And the digital technology not only is fast and responsive, but it can also collect quite a large amount of data and communicate that data through a building automation system or locally at the controller. Plumbing Engineer magazine surveyed engineers not long ago to ask them why they specify digital mixing. The respondents rated various features between 1 and 5 from high to low value. The number one reason engineers specified digital mixing was because of the outlet temperature control, or the tight temperature tolerance provided by high-speed actuation and fast response sensors. So that plus or minus 2 degree tolerance is the top reason engineers went with digital mixing. Building automation integration was number 2. Essentially, it's the ability to communicate with the system to control or monitor valve performance, energy consumption, temperatures, and pressures through either Modbus or BACnet protocols. And next is remote temperature monitoring and the ability to remotely change temperature set point, which are features of integration with a building automation system. The sanitization mode, web accessibility, and data logging fill out the set of reasons engineers choose digital mixing. So let's reiterate the benefits of digital mixing. Tighter control over mixed outlet water delivery, far superior system management because it allows tying digital tempering into pump control, simplicity of install, repair, and maintenance. Many are plug-and-play systems that become pre-assembled, pre-calibrated, pre-tested, and pre-wired. It's simply a matter of making water connections and bringing power to the controller. And as we talked about, there's the opportunity for conserving energy and better energy costs. Some of these systems can monitor mixed outlet flow and energy consumption. They have communications capability and the sanitization mode for high temp purges, which we've already talked about. All of these capabilities result in minimized risks for facilities, safer facilities for occupants, mitigated liability for the owners, and cost-efficient management of the hot water delivery system overall. So now to provide some context, this depicts a digital mixing system that would be down in the mechanical room off the boiler. It shows in a simplified way the entire system, providing safer, more efficient water delivery from the point of source to the point of use. You can run hot water at elevated temperatures to mitigate the risk of Legionella and other waterborne bacteria, and you can protect users and bathers at the point of use with thermostatic mixing valves at showers, sinks, eye wash, and drench stations throughout the entire facility. Here's a look at a specific digital mixing solution, the Powers IntelliStation. A control module provides the overall intelligence. The panel comes fully assembled, calibrated, tested, and pre-wired. There are temperature and pressure sensors throughout the system. It provides the ability to measure inlet and outlet temperature and pressures, the ability to do that on the return line as well. There's a pump that an engineer can specify, and there's an optional flow center package which allows the facility to monitor the mixed outlet flow and return flow, so overall energy consumption can be measured. To review, some of the key features of IntelliStation include tighter temperature control to plus or minus 2 degrees Fahrenheit of set point, a 0.5 GPM minimum flow, which requires a recirculating pump. So if you think about that, in a large system, you can control temperature down to a half a GPM, and the IntelliStation can control the pump, turning it on and off based on return target temperatures that are set up when the system is commissioned. There's also a high temperature sanitization process, and the IntelliStation is easy to install and adjust. There is no special drivers or software required or a laptop computer. Installation takes place and commissioning takes place at a password-protected unit. Building automation is also native to the controller. There's no separate modules required to integrate into a building automation system. In summary, digital water mixing has, as we've seen, numerous advantages, with 3 of the most important ones being, number 1, precise temperature control, Number 2, communication ability through integration with a building automation system. And finally, it helps promote the more efficient use of energy, resulting in lower energy costs. And ultimately, that creates peace of mind. Thank you. Now, if you have any questions, I'd be happy to answer them.